Hello class, in this video we will be performing stoichiometry calculations involving excess reactants. In most chemical reactions, the number of moles for each reactant is usually different, where you normally have one of the reactants getting depleted first. Let's have a look at the combustion reaction down below. In this example, you've got 3 moles of fuel with an unlimited supply of oxygen gas. Hypothetically, let's say that 1 mole of fuel and 1 mole of oxygen reacts to produce 1 mole of carbon dioxide and 1 mole of water vapor. This reaction will continue to occur until one of the reactants gets completely used up, and at that point, no more products can be formed. In this example, we can see that all of the fuel, in this case being the wood, gets used up before oxygen does, and we can only produce a maximum of 3 moles of CO2. It doesn't matter if we had extra oxygen in this reaction, because the products cannot be formed unless we've got more fuel. We define the reactant that gets completely used up first in the chemical reaction as the limiting reactant. Hence, fuel is a limiting reactant in this example. The limiting reactant will always determine the maximum amount of product that can be formed. In contrast, we refer oxygen as the excess reactant because it doesn't get completely used up in the chemical reaction. Because we are interested in the carbon dioxide emissions from the combustion of fuel, it will be an important skill for us to calculate what is the maximum amount of CO2 produced from a given set of starting materials. To identify the limiting reactant, we need to follow 4 steps. Firstly, we need to write a balanced chemical equation so we can see the stoichiometric ratios. Secondly, we need to calculate the number of moles of each reactant. From here, we then use the mole ratios to calculate the theoretical amount of each reactant from the known substances. And finally, we then compare the ratios and search for the lowest quantity to identify the limiting reactant. This will make more sense by going through an example. In this example, we are already provided with the balanced chemical equation, so we can skip step 1. In this example, let's say that we've got 25 grams of hydrogen and 100 grams of oxygen. To find the limiting reactant, we calculate the number of moles of each substance. From here, we need to use mole ratios to calculate the number of moles of the other reactant required from each known amount. In this example, we know that there's a 2-to-1 ratio between hydrogen and oxygen. Since we've got 12.5 moles of hydrogen gas present, this means that the number of moles of oxygen gas should be half of this amount, hence the amount of oxygen consumed should be 6.25 moles. If we look at this ratio, hydrogen gas cannot be the limiting reactant because we only have 3.125 moles of oxygen. Let's now use mole ratios for the other known substance. In this question, we've got 3.125 moles of oxygen, and if we use mole ratios correctly, the amount of hydrogen should be twice the amount of oxygen, hence there should be 6.25 moles of hydrogen gas reacting. If we take a closer look at the second ratio, I'm hoping that you can see that oxygen will be completely consumed in the reaction, and only 6.25 moles of hydrogen gas from the original 12.5 moles was consumed in the reaction. As a result, oxygen gas is the limiting reagent. Have a go with a similar problem and identify which of the following substances is a limiting reactant. Pause the video now and resume the video again when you're ready to compare answers. To begin, we need to write a balanced chemical equation for the combustion of propane. We then need to calculate the number of moles of each reactant by dividing the given mass with the respective molar mass. What I'll do next is I'm going to use mole ratios to find the calculated ratios using each known substance. In this question, we've got 0.336 moles of propane, hence the amount of oxygen required to completely react with propane should be 5 times this amount over here. Based on this ratio, we know that propane cannot be the limiting reactant at all because we need 1.68 moles of oxygen when we only have 1.075 moles. In contrast, the amount of propane that completely reacts with 1.075 moles of oxygen can be found by dividing this amount over here by 5, giving us an answer of 0.215 moles. If we compare the second ratio to the amount of starting materials that we've got, you should be able to identify that oxygen is a limiting reagent because oxygen gets completely consumed while there's going to be an excess amount of propane that's unreacted. Let's go through a slightly more challenging example. In this question, we want to calculate the volume of carbon dioxide produced in liters when 65 grams of butane undergoes complete combustion in 200 liters of oxygen measured at standard laboratory conditions. The first part of this question wants us to identify which reactant is a limiting reactant. We begin by calculating the number of moles of each reactant. To calculate the number of moles of butane, we divide 65 with its molar mass, giving me an answer of 1.12 moles. To calculate the number of moles of oxygen gas, we're going to be using the formula N is equal to V over Vm, where Vm is going to be equal to 24.8 under SLC. Entering these values into the calculator should give you an answer of 8.06 moles. From here, we need to use molar ratios to calculate the theoretical amount of reactants that would be consumed from each known substance. From the 1.12 moles of butane gas that we have in this reaction, the amount of oxygen gas needed to completely react would be 7.28 moles, which is found by multiplying 1.12 by 13 over 2. If we examine and compare this ratio over here to the actual quantities of each reactants that we have, we can easily see that butane is going to be the limiting reagent for this reaction because butane gets completely consumed while there's some left over of oxygen gas that is unreacted. Similarly, we could also perform mole ratios using the known amount of oxygen gas to confirm this as well. The amount of butane that reacts completely with 8.06 moles of oxygen gas is 1.24 moles. Based on this ratio over here, we can see that oxygen cannot be the limiting reagent at all because we only have 1.12 moles of butane, not 1.24 moles, thus proving that butane is the limiting reagent. Let's now answer part B. Part B of this question wants us to calculate the volume of carbon dioxide formed. To do this, we need to use mole ratios with the limiting reactant because this determines the maximum amount of products formed. Hence, I've set up a ratio between carbon dioxide as my unknown on the numerator and butane gas, which is the limiting reactant, on the denominator. The number of moles of carbon dioxide produced should be 4 times the number of moles of butane, which would therefore give us an answer of 4.48 moles of CO2. Because the question ultimately wants us to calculate the volume of gas measured at SLC, we will need to use the formula V equals to N times Vm. Multiplying 4.48 moles of CO2 with the molar volume will give us an answer of 111 liters of carbon dioxide gas. I would now like you to answer 2 similar questions to gain further practice. Pause the video now and give yourself around 2 minutes to calculate the mass of CO2 produced. Resume the video again when you're ready to review your answer. Firstly, we begin the stoichiometric process by writing the complete combustion equation for ethanol. Secondly, we can then calculate the number of moles of each reactant by dividing mass with the respective molar mass. From here, we're going to be using mole ratios to calculate the theoretical amount of reactants required for the reaction. With 0.446 moles of ethanol, the amount of oxygen required should be 3 times this amount as stated in the mole ratios. If we look at this ratio, you should be able to tell that ethanol is going to be the limiting reagent because it gets completely consumed and there's an excess amount of oxygen that did not react. We can further prove this by performing mole ratios with a known amount of oxygen, where we can see that oxygen cannot be the limiting reactant because we will need to have 1.04 moles of ethanol, which we do not have. Since we know that ethanol is the limiting reactant, the number of moles of carbon dioxide produced should be twice the number of moles of ethanol, giving us an answer of 0.891 moles. Because the question wants us to calculate the mass of carbon dioxide produced, we're going to multiply 0.891 moles with its molar mass, giving us an answer of 39.2 grams when corrected to 3 significant figures. Have a go with the last question. Pause the video and resume again when you're ready to check your answer. To answer this question, I'm going to take on a slightly different approach. What I'm going to do is I'm going to calculate the theoretical amount of hydrogen chloride produced from each known amount of reactant provided. According to the stoichiometric ratio, the amount of hydrogen chloride produced from 3 moles of hydrogen gas should be 6 moles. From 2 moles of chlorine gas, we should have 4 moles of hydrogen chloride produced. Because the limiting reactant gets completely consumed in the reaction, the maximum amount of product to form will be dependent on the limiting reagent. As a result, only 4 moles of hydrogen chloride can be produced from this reaction because the reaction can no longer proceed and no more products can be formed once chlorine gas is completely consumed. Hence, the amount of unreacted hydrogen gas will be 1 mole because 2 moles of hydrogen gas had to react with 2 moles of chlorine to produce 4 moles of HCl. Hence, D is going to be the correct answer. By now, you should be able to meet the success criteria in this video. If you found this video helpful, please give it a like. Thank you for watching and I'll see you guys again in the next one. Bye.